Hello everyone, my name is Faris Abdulrazik, and today I'll be teaching you a little bit about UV VIS spectroscopy. Alright, let's get into some background. So spectroscopy in general is the study of how light particles, otherwise known as photons, affect atoms and molecules, and it also investigates the varying reactions that different types of light have to different types of atoms and molecules, and how different atoms and molecules react to the same type of light. So I'll be focusing specifically on UV vis spectroscopy, which is spectroscopy dealing specifically with light with the wavelength values in the ultraviolet or visible region of light, which is usually between like 200 to 800 nanometers on the electromagnetic spectrum. And the electromagnetic spectrum includes like all types of lights. You got gamma ray, infrared, all types of rays, and the UV vis. Actually, the visible region is just like a really small part of the whole electromagnetic spectrum, and that's what a UV vis spectroscopy focuses on. So, what it does, it looks at the wavelength of light that's absorbed using an absorption spectrum by a compound. So the instrument that's used to study UV vis spectroscopy is called a UV vis spectrophotometer, and basically you input a compound and you are outputted this. So this is just an example. So for example, this compound is inside the instrument, and then it looks at the amount of light that's absorbed. So at the maximum amount of light absorbed, the nanometers, the wavelength of that light is 395 nanometers. All right, let's now get into the intricacies of how a UV spectrometer would uh, take in the light and input that absorption spectrum that I was showing you earlier. So it's actually not too complicated. So basically, a beam of light is emitted. It's from the visible or a UV light source. It could be both. Um, then it is separated into component wavelengths using like some kind of prism, which like diffracts it. So that's what you see there. And then basically all the beams, um, they kind of split equally. So one of them um, is it like goes through a small container. It would be this container right here, and then it contains a solution of the compound you're studying. So whatever compound you're looking at, the absorption is, it it contains part of that solution, and then the other beam goes into the same curvette, but it only contains the solvent. So then it just used some like electronic detectors or like to look at the measurements so that they can measure the intensity. And then what's outputted is the intensity of the light beam or the light absorption. Um, the reference beam, which is the beam that goes through the solution that contains the compound, has um, no light absorption, and it's defined as this I of 0. And then the intensity of the sample beam, which is the beam that went through the curvette with only the solvent, has an intensity of I, and it's whatever value is the absorption. And then the spectrometer like gets all the wavelengths, it records all the wavelengths, and look at a more in-depth version of what we call the UV absorption spectra. Is different from the UV absorption spectrum. There are two different things. I'm going to be basically explaining this graph. Anyway, So the energies that are noted in this graph are more like regions rather than specific um, values. Basically, they are what is considered sufficient enough to excite a molecular electron into the next orbital. So electron excitation. So um, the another word for like the absorption spectroscopy we're looking at right now is called electronic spectroscopy. So the diagram that we're looking at shows the various kinds of electronic excitation that can occur in the molecule that we're looking at. So there are six different transitions that are possible. The two ones that uh, need the least energy are from a non-bonding to an anti-bonding, and from a bonding to an anti-bonding. Um, they are the blue colored transitions, and they are achieved by the energies in the UV uh, visible region in the electromagnetic spectrum. Um, the energetically favored electron will be from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. And then you have something called the excited state, which is what's left over. So, in regards to UV vis spectroscopy, when these molecules are exposed to light that have an energy that is uh, big enough to allow for this transition or excitation, some of the light energy will be absorbed in order to promote the molecule to the higher energy orbital. So what we were looking at records the wavelengths at which the absorption occurs, and then at the same time records the degree of absorption at each wavelength. So technically, the only possible transitions in UV vis spectroscopy is the blue arrow ones, because they are the ones that are able to happen with the energies that are in the UV visible region of the electromagnetic spectrum. Um, so now I'm gonna go through some of the applications of UV vis spectroscopy, mainly in the real world. As I mentioned before, the absorption is useful for finding concentrations of compounds. Using a law called Lambert-Beer law, it states that there's a direct relationship between light absorbed and the concentration. So they can look at the light absorbed and determine the concentration of a substance. Um, so one of the examples is drinks like this. The FDA mandates a certain level of caffeine that is allowed, because caffeine is a drug and too much of it can actually be harmful to its consumers. So one of the ways that these companies determine how much caffeine their drink has is UV spectroscopy. And it's also used with olive oil. If you ever gone to the supermarket and it was like going through the olive oil, if you've ever wondered why some olive oil is extra virgin, others are virgin, and then some is just olive oil, those titles are identified by looking at the concentration of the fatty acids or the saturation of the fatty acids in olive oil. Um, Looking at if it's unsaturated, it's considered extra virgin olive oil, very, very pure olive oil, and so forth and so forth. It's also used to identify a multitude of compounds, since most compounds' molecular structure uh, have a value on the absorption spectrum. By looking at how much light a compound absorbs, you can uh, line it up to the different compounds and easily identify it. Um, it is also used one way, more specific, is analyzing sunscreen and its like effectiveness. Um, but yeah, that's an overview of UV vis spectroscopy. It is a little complicated, but basically just dealing with how lights in the UV, ultraviolet and visible region of the electromagnetic spectrum affects molecules and has some really useful applications. Thank you for listening, and I hope this taught you something about UV vis spectroscopy.